All right. Hi guys, if I sound tired, it's because I am. This is actually my third time trying to record this video. The first two times, the iPad stopped working. This is an iPad from school. Turns out that children had taken a million different pictures, enough to fill about 20 gigs of space, and all the space ran out on the iPad. And so it looked like it was recording, but nothing happened. So by the time I figured out what its problem was, now it's my third time recording this. So a little tired. It's like 10 o'clock at night. And yeah, I'm tired. So did I say I'm tired? I'm tired. So where I am in this is I am in section 10.3. And I'm talking about the idea of static equilibrium. Static equilibrium is the idea that an object is not in any kind of motion. There is no translational motion, so it's not moving left, right, up, down. And there is no torque or rotational motion happening either. So that means all the forces added together will equal 0. And all the torques added together will give you 0. These questions get long. So there's actually two model problems. I'm going to do one of them in this video and give you a few to try. And then likely what will happen is you will have questions. And so I will make a video answering those questions and doing the second model problem. That's kind of where my brain is for this right now. And in the first video, I really talked about kind of what our plans are moving forward. So you should have already watched that. It had the answer to number 30 that a lot of you had. And it had kind of thoughts going forward. So static equilibrium means that all the forces added together equal 0. And all the torques added together have to equal 0. Now, wherever there is a force, there is also a torque to go with it. Wherever there's a force, there's also a torque. So in this example, it's my third time doing this. In this example, we have a firefighter who's standing 2/3 of the distance up a 4-meter long ladder. So the length of the ladder is 4 meters. Dude is standing 2/3 of the way up the ladder. So if you take and you multiply 4 by 2/3, 4 by 2/3, it gives us 2.666. So the length to the firefighter is 2.666, on and on and on. All right? Now, it says the mass of the ladder, I've almost got this memorized, is 35 kilograms. And the mass of the firefighter, with all his gear and everything, or her gear, is 95 kilograms. And the angle that the ladder makes with the ground is 58 degrees. Now, the question that it asks is, what does the coefficient of static friction have to be to keep the ladder from moving? In other words, to keep it in static equilibrium, because if you're walking up a ladder, you don't want it moving. So there's a lot to this. So if I draw a diagram here, okay, if I draw a diagram, and I'm going to have to, here's the dude 2/3 of the way up the ladder, okay. There is a force of gravity on the firefighter. There's a force of gravity also on the ladder. We always consider force of gravity to be at the center of the object. So the center of the ladder would be right about here, 2 meters up, because the full length of the ladder is 4 meters. So this would be the force of gravity on the ladder. This angle is 58 degrees. But there are some other forces going on that we haven't really talked about much. There is a force of friction going that way because there's friction trying to keep the ladder in place. Wherever there's a force of friction, there's also a force working against it. In this case, there is a normal force that the house is exerting on the ladder. Think about if you lean a ladder up against a wall. What keeps the ladder from going into the wall is the fact that the wall is pushing back on the ladder with equal force. That is a normal force of the house or the building on the ladder. There's also, why doesn't the ladder sink into the ground? Well, because there is a normal force that the ground is exerting on the ladder. Those are all of the forces that are happening. Now, some of them are going horizontally and some of them are going vertically. So the one we want to talk about coefficient of friction. So that means we want to talk about friction. So eventually we want to be talking about the horizontal forces. But that's actually going to be the last thing we talk about. We have to talk about a whole lot of things before we get there. And you'll see why when we get there. The first thing we're actually going to do is we are going to look at the forces in the y direction. In other words, we're going to look at the forces going vertically, up and down. There are 3 of them. And just like always, we're going to consider up positive and down negative. So the normal force that the ground is exerting on the ladder is going up, so it's positive. The force of gravity on the ladder is going down, so it's negative. And the force of gravity on the firefighter, we'll put 2 F's for firefighter, is also going down, so it's negative. And all of those forces have to equal 0, because hopefully this ladder is not moving up or moving down, so the net force would be 0. So there's no formula for this, and I don't know what it is. But force of gravity on the ladder is the mass of the ladder, which is 35, times acceleration due to gravity, which is 9.81. Force of gravity on the firefighter is the mass of the firefighter, which is 95, times acceleration due to gravity, which is 9.81. So I can actually figure out what the normal force of the ground on the ladder is by moving those over to one side and working that out. So 35 times 9.81 plus 95 times 9.81 gives me the wrong answer. I did something. Oh, I pushed the wrong button. It turns out to be, I'm going to cheat, 1,275.3 newtons. Now, I'm not worried about significant figures because that's not my final answer. That's just a piece of the information that I needed to figure out my answer, because remember, ultimately I'm looking for the coefficient of friction. So I've looked at my forces in the y direction. Now I'm going to switch gears a little bit, and I am going to look at all the torque that are happening, all the different types of torque that are going on. Again, if this is in static equilibrium, all the torques added together should give me 0. So everywhere where there's a force, there's a torque. Everywhere. So what I want you to visualize is if this ladder was stuck to the ground at that point, that would be like the hinge on a door. That would be the pivot point. If you have a seesaw, that would be your pivot point. That is where this thing is going to move, either clockwise or counterclockwise. Now remember that torque is lever arm distance times the force. So lever arm distance is how far away is the force to the pivot point. That's what it wants to know. So we don't look separately at torque from like horizontally and vertically. We look at them all together. But what we do is we give each one a sign based on whether that force would create a rotation in the clockwise direction or the counterclockwise direction. Clockwise direction means that the torque would be negative. Counterclockwise direction means that the torque would be positive. So let's look first here. If we have a force, a normal force on the ground, we also have a normal torque. We also have a torque from the normal force on the ground. Now, again, picture it. If the only force, if there were no other forces, and we pushed that ladder up, it would rotate this way. It would start going that way. All right, think about a little gopher sticking his head up right where that is. It's going to go ping, and it's going to make it start rotating in that direction. So because it's going in the clockwise direction, that torque is negative. Now, there's also going to be a torque because of friction. Now, think about if I push on the bottom of this ladder, what's going to happen if I push this in? This end's going to go this way, and it's actually going to spin this way, right? If I push, the force of friction is pushing in that way, that's actually going to make the ladder go counterclockwise, which means the torque from the friction is actually positive. So moving on, we are going to have a torque because of the force of gravity on the ladder. So we're going to have a torque because of the force of gravity on the ladder. Now again, if this was the only force pulling and it was hinged here, what would happen is the ladder would start turning that way, which is clockwise, which means this torque is negative. We would also have a torque because of the gravity on the firefighter. And again, think about it. If this was the only force working and the ladder was hinged here, it would actually pull it that way. So again, negative. Final torque is torque from the normal force of the house pushing on the ladder. So think if the only force was the house pushing on the ladder, it would actually make it go counterclockwise, which is a positive torque. Now they all have to equal 0. So that was a lot of work, and we haven't even put numbers or formulas in here yet. So let's go through each of these torques and come up with some numbers to put in here. For this, we know it's negative. Now, the R, remember that this is R times the force. We already know the force. The force is 1,275.3. But what's the lever arm distance? How far away is this force from the hinge point? Well, it's not any distance away. It's right where the hinge point is. So that's 0. So this actually just works out to be 0 anyway. I like it. Plus, okay, let's talk about this. We don't know what the force of friction is. We don't have any idea. But it doesn't matter that we don't have any idea, because again, how far away is this force from the hinge point? It's no distance away, so my lever arm distance is 0. So again, that's 0. So far, all I have is 0. Minus, this is not going to be 0. So here we have torque because of gravity on the ladder. So here, we know if we just look at this little triangle here inside it, I'll take that out and I'll write it down here. If we just have that little one here, we know that this distance is 2 because gravity is working halfway up the ladder. The full ladder is 4 meters, and so halfway is 2. This angle is 58. This is force of gravity, and this is my lever arm distance, and they are perpendicular to one another. So if I want to know what R is, that's the adjacent side. I know the hypotenuse side, that is cos. Cos of 58 is R over 2. So 2 times cos of 58 is my R. So for here, my R is 2 times cos of 58 times my force. Now my force is the force of gravity on the ladder. So the mass of the ladder is 35 and acceleration due to gravity is 9.81. I'm going to use the same logic here to figure out the torque on the firefighter. So this time, this triangle's a little bit bigger because he's standing 2/3 of the way up the ladder. And again, we said that 2/3 of the way up the ladder is 2.66. We have the gravity here. So all of this logic stays the same. It's just that this is 2.666. So my R, 2.666, you could keep going, times cos of 58 times my force. Now my force is the force of gravity on the firefighter. So the firefighter is 95 kilograms times 9.81. I'm running out of space because this is so long, so I still have to do the normal force on the house. This is the one that is a little bit more complicated. It's also the one that your textbook gets wrong, and it consistently gets it wrong all the way through. So on the example that it does, it gets it wrong. In the questions that it does for you, it gets it wrong. I know it gets it wrong because I have gone to university lecturers on the internet. I've looked up different explanations and they all say this is wrong. And I had sort of already figured that out myself, but I confirmed it with people who know more than I do. So the textbook has it wrong. So think about this, okay? And I don't know how I'm gonna, okay. So normal force on the house is going this way. So let me just write that down here. Normal force on the house is going this way. If the normal force on the if the force is going that way, the lever arm distance, the R, has to go that way. And this, we know, has to be 4 because the distance of this triangle is 4, and these are going to be congruent triangles. So there's a right angle here. If this angle is 58, this angle is 58. So this R is actually the opposite side, not the adjacent side. So in this case, I would say sine of 58 is equal to R over 4. So 4 times sine of 58 is my R. In your textbook, they say cos. They're wrong, okay? They're not right. So plus, and I'm going to have to put this down here, lever arm distance is 4 times sine of 58 times my force. Now my force is the normal force on the house, and I don't know what that is. But I know that the whole thing has to equal 0. So now this is an algebra problem because I only have one unknown in this whole thing. Because this is 0, it's gone. This is 0, so that's gone. So if I move this over to one side, I'm going to have normal force on the house is 2 times cos of 58 times 35 times 9.81 plus 2.66 times cos of 58 times 95 times 9.81, and then, so I've got this over on one side. So now, to get this by itself, I'm going to have to divide by 4 times sine of 58. So, normal force on the house. I've done this 3 times. I know, I think it's like 400 and something, but I'm going to do it again anyway. 2 times cos of 58 times 35 times 9.81 plus 2.66 times cos of 58 times 95 times 9.81 of that divided by 4 times sine of 58 gives me 494.5, and it keeps on going. So normal force on the house is 494.5. Yay, that's wonderful. So now, I have figured out the normal force on the house, which is going this way. I have figured out normal force of the ground, which is going up and down, and I want to know the coefficient of static friction, which is keeping this ladder from moving. So force of friction is going across horizontally. So that is a force in the x direction. It's going across. So I'm going to look at those forces now. Again, those forces added together should equal 0 if this is in static equilibrium, which we certainly hope it is. So we have force of friction going that way. It's going to be positive. We have normal force of the house going that way, so that's going to be negative. And those are the only two forces going horizontally, so the net force should be 0. So really, force of friction is equal to normal force on the house. Now, force of friction is coefficient of friction times the normal force going up and down. The normal force going up and down is 1,275.3, and that's equal to the normal force on the house, which is 494.5. So the coefficient of friction, once I divide both sides by that, is 0.39. That makes sense because the coefficient of friction should be between 0 and 1 and should be relatively low, and it is. So yes, this is long. I agree. You are probably now yelling at your screen. I'm sorry. You may have to watch this a couple of times before this makes sense. You may have to watch it as you do the questions. I will be posting this, but you are going to do page 501, 31, 32, and 34. You're not going to do 33 because I want to do example number 2 with you before you attempt that. All right, so have a good night. I'm going to try and get these uploaded before I go to bed, and we'll see you tomorrow.